Okay, in this lesson we're going to be talking about how to factor using a difference of squares. By the end of this lesson you should be able to solve equations that involve differences of squares. When we're solving differences of squares equations, it's important to be aware of what we do when there's fractions. So if you recall, when we factor differences of squares, this is when when you have two terms, so when you have a binomial, where the first term is a perfect square and the second term is a perfect square, and they're separated by subtraction. And how we factor that was to square root the first term, square root the last term, the second term, and then rewrite it as the product of a sum and a difference. Now, when there's fractions, you want to be aware of fractions that are perfect squares. That's when the numerator and the denominator are both perfect squares. So if we look at the square root of 4t squared and 25, both the top and the bottom are perfect squares, and so I could just square root them, and my answer would be 2t over 5. We square root the top, the numerator, and the denominator. The other way that you could deal with fractions when we're dealing with differences of squares is you could clear them from the beginning by multiplying both sides by the denominator, or by the common denominator if there's more than one fraction there. That would allow you to solve the equation without having to deal with fraction operations. When we're factoring, so before we solve the equation, we always factor it first. We need to look at our strategies for factoring. So the first thing we do is we pull out the GCF. So look for your greatest common factor. That's the very first thing that you want to do each time, is to look for a GCF, and then pull that greatest common factor out. And then depending on the number of terms that are remaining, you could factor by grouping. You could use product, sum, guess and check, or MAC when there's 3 terms. There's 2 terms and they're separated by subtraction. It may be a difference of squares. And so once you've done this part, once you've done the work of factoring and you've factored it completely, then you'll use the zero product property to solve. And remember, the zero product property says, hey, set each of your factors equal to 0 and solve for the variable. Now typically we'll have 2 solutions, but there are occasions where we have less and there are occasions where we have more. So remember that your solutions are going to come from each of the binomials, and then you may have an additional solution that comes from the greatest common factor. If the GCF has a variable, so when you factor out the GCF, if there's a variable, then it will that variable, okay, that GCF will be where you get your third solution, and 0 will be the solution that you get there. If the GCF is a number, okay, so no variable, such as the bottom one where we have 3 times y plus 2 times y minus 3, no variables on that GCF that they pulled out. So that would not be included in your solution. So you would just have the 2 solutions there. So be aware of GCFs that have a variable because it's going to give you an additional solution for your factors. All right, so let's solve the following equations by factor. So I look at A, and I know this is a difference of squares. There's 2 terms here. The first term is a perfect square. The last term is a perfect square. And it's separated by subtraction. I still want to look for a greatest common factor, even if I have a difference of squares. So I'm looking at 9 and 4. There's no GCF between that. So I'm just going to factor this how we would factor every other difference of squares. I know that my solution is going to be the product of a sum and a difference. The first term in each of my binomials is going to come from the first term by taking the square root of 9n squared. So the square root of 9n squared would be 3n. And I know the second term of my binomials comes from taking the last term by square rooting the last term. So that would be the square root of 4, which would be 2. And so we would have 3n plus 2 and 3n minus 2. So I factored it. So my factors are there. And then we set each factor equal to 0 and we solve. So I have 3n plus 2 equal to 0. I have 3n minus 2 equal to 0. And we're going to solve it. So on this first one, I would subtract 2 on both sides. So that would give me 3n is equal to negative 2. And then divide by 3 to give me negative 2/3. On this one, I would add 2. So that's 3n is equal to 2. And then divide by 3. So that would give me n is equal to 2/3. And then remember that we're going to write our solution as a solution set. It would be negative 2/3 and positive 2/3. Don't forget to go back and check your solution in the original equation to make sure that what you solved for is correct. In this next one, we have 4x squared equals 16. So before I solve this one, it's going to be important that we get them on the same side. So we subtract 16 on both. It's going to be 4x squared minus 16 is equal to 0. Now, I look for a greatest common factor. So remember, even if we know that it's a difference of squares, we still want to look for a GCF first. So my greatest common factor here would be 4. I could factor out a 4 from both terms. So if I factor out a 4 from the first term, that leaves me with x squared. If I factor out a term of 4 from the second term, that leaves me with 4. So I still have a difference of squares here, but now I've pulled out the GCF, so I'll know that both of my factors are indeed in simplest form. So we've got 4 times, again, we're square rooting the first term, so that's x, square rooting the last term, which is 2. And so my two new factors are x plus 2 and x minus 2 equals to 0. Now, remember that we said pay attention to the GCF. If the GCF contains a variable, it's going to give us an additional solution. Since 4 does not have a variable attached to it, I don't need to worry about it when I'm looking for my solution. So, we're going to use zero product property, so I set my two other factors equal to 0. Since x plus 2 equals 0, x minus 2 is equal to 0. And we subtract 2, that gives me negative 2. We add 2, that gives me x is equal to 2. And so my solutions for this one would be negative 2 and 2. Again, you want to check it back in the original equation just to make sure that what you get is the correct solution. All right. So here we have, again, a difference of squares. So let's look at this first one. We have a squared minus 25 over 36. This fraction is a perfect square. So 25 and 36 are both perfect squares. So I could solve this using difference of squares. So if I'm doing that, remember that we're writing two binomials. It's going to be the product of a sum and a difference. The first term comes from square rooting the first term, so square root of a squared would be a. The last term, the second term, comes from square rooting the last term. So if I square root, if I take the square root of 25 over 36, that'd be the square root of 25, which is 5, over the square root of 36, which is 6. So I'd have a plus 5 over 6, and I would have a minus 5 over 6 is equal to 0. And then I'd solve. So a plus 5 over 6 equals 0. A minus 5 over 6 equals to 0. I subtract on this side, so that's a equals negative 5 over 6. I add on this side, that's a equals positive 5 over 6. And so we get our solution to be negative 5 over 6 and positive 5 over 6. Again, you want to go back and check your solution just to make sure that you are good. Now, on this one, we have 18 minus 1/2 x squared. So, I know that this is not a difference of squares yet, because 18 and 1/2 are not perfect squares. So I go about solving this one by clearing the fraction first. So I'd multiply everything by the denominator, which is 2, both sides. So 18 times 2, that would give me 36, minus the 1/2 would go away with the 2. They would cancel each other out. So that leaves me with x squared. And 2 times 0 is 0. And so now I have a difference of squares. Again, take the square root of the first term, which is 6. Take the square root of the second term, which is x. So I have 6 plus x, and I have 6 minus x is equal to 0. We said each of those equal to 0. So that would be 6 plus x is equal to 0. 6 minus x, which is equal to 0. Here we would have x is equal to negative 6. And here we would have negative x is equal to negative 6. So that would mean x is equal to positive 6. And so we see our solutions here are negative 6 and 6. again, you want to go back and check your solution just to make sure that everything matches up. Again, when we're solving, factoring out this GCF, so again, we want to make sure that everything's on the same side. So I'd rewrite this equation so that 50 is on the same side, so subtract it on both sides. Factor out your greatest common factor, so we have a GCF of 2. So that would give me x squared minus 25 equals to 0. Once I factor out the GCF, I see that, hey, the inside is a difference of squares. So again, square root the first term, it gives me x. Square root the last term, that gives me 5. And then write that as the product of the sum and difference. Again, if this had a variable on it, I would use it to find one of the factors. Because it doesn't, I'm not going to worry about that part. We have x plus 5 is equal to 0. We have x minus 5 is equal to 0. So it gives me x is equal to 5, negative 5, and x is equal to positive 5. So I see that my two solutions here are negative 5 and 5. We're looking at, alright, when we look at B, again, we're doing the same thing, so get 48r on the same side with 3r cubed. And then factor out the GCF. So the GCF here would be 3r. So you factor out the 3r, that's r squared, minus 16, because we pulled out an r here, is equal to 0. Again, once I factor out the GCF, I can see, hey, this is a difference of squares on the inside. Okay, it would be factored into r minus 4 and r plus 4. I'm going to switch the order of that. It's no big deal. Okay, here, because the GCF has a variable in it, we're going to set all three of them equal to 0. So we'll have 3r equals to 0. We'll have r minus 4 is equal to 0. We'll have r plus 4 is equal to 0. I solve each one. R equals 0. R equals 4. R equals to negative 4. So we see our three solutions are negative 4, 0, and 4. Okay, so here's our super problem. So we're going to solve this equation using a difference of squares. So in this problem, we have 4 terms, so we're going to want to factor this by grouping. So I group my first 2 terms together, I group my second 2 terms together, and I pull out the GCF in each of them. So in the first one, I can pull out a 5x squared, which leaves me with x plus 3x. No, this leaves me with x plus 3. And the second one, I can pull out a negative 5x from both. So that leaves me, or negative 5 from both, which leaves you with x plus 3. And so I have 5x squared minus 5. I have x plus 3. Those are my 2 factors. I can also factor out another 5 from this first group. So if I factor that out, that leaves me with x squared minus 1 and x plus 3. Now, we have a perfect square, difference of squares here, because x squared and 1 are both perfect squares. So that could be factored into x minus 1 and x plus 1. Square root of the first term, square root of the last term, write it as the product of sum and difference. And then x plus. So this would be considered our super problem. This is how we factor that one. And then when we're factoring, remember we need to look at the GCF. So because there's no variable on this GCF, I don't need to worry about using that to find one of the solutions. And then my 3 binomials here would be my solution. So x minus 1 equals to 0. X plus 1 is equal to 0. And x plus 3 equals to 0. And so we have our solutions as being x is equal to 1, x is equal to negative 1, and x is equal to negative 3. And so in set notation, that would be negative 3, negative 1, and 1. This is how we solve difference of squares equations.